So hi everybody. So we are going to start. Welcome to this meeting. It's been a while. We didn't have this kind of meeting to give you general news about the project and about the upcoming gravitational wave run, the so-called O4 run. So today I propose to you this agenda to try to give you the latest news about the Kilonova-Catcher project. And then we will directly move to some reminders about last updates and reminders about the gravitational wave O4 run that is coming in 1 month now. So, and we will tell you what are our objectives in terms of science. And then we will try to go through the astronomer guide you may have read now to see what is the typical follow-up strategy we envision for to follow up mainly binary neutron star mergers event. How we plan to organize ourselves in terms of alert release, latency for making follow-ups, and how to send your images to QandA for scientific analysis. And if I am short, I hope to let you have some time to ask free questions, and even if you want to have free discussions about some topics related to Kilonova-Catcher, you will be free to take this time for this. Okay, so let's go for the for the first section. Sorry. So the news about the Kilonova-Catcher project. So I don't know if we have newcomers. In case you have a question you really want to ask, you can raise your hand if you want. I will make some stop at the different sections so that you can ask questions if something seems weird to you. So for the very newcomers, I just wanted to give you very quick reminder about the QandA collaboration. Sarah is connected, so you could correct me, Sarah, if I say wrong things, because Sarah is the scientific responsible of the QandA collaboration. That is the collaboration that group 29 institutes over the world. I think it's like we are distributed over 18 countries. And this is what I saw in the last publication we've made. I hope these numbers are correct, but we are able to trigger observation on 23 observatories, and it represents about 30 telescopes of different kinds. Some are completely robotized telescopes, some are more remote control telescopes, and well, we don't have manual telescopes, but some are able to make spectroscopic observation, and some are able to only make photometric observations. And we have telescopes with, let's say, 25 centimeters diameter up to 1 meter diameter, roughly. Who is caché? So we also have access to large facilities, such the CFHT telescope here, which is a 3.6 meter telescope, if I remember well, in the Hawaii Island. And we have been granted some time also for spectroscopic observation at the very large telescope here in Chile, in Paranal. Okay, this is a global overview of what is the QandA collaboration. So inside you have plenty of people. We are like tens of people with different expertise, theoreticians, observers, people who make gravitational wave studies, model, also electromagnetic specialist of electromagnetic counterpart of multi-messenger sources such as gravitational wave sources, but also gamma ray burst, supernova, and other kind of very energetic transient events. For the Kilonova-Catcher team, so we have people from QandA, of course. So you have me here. So I am Damien. I am working at CA near Paris in Saclay. So let's say Paris-Saclay. You have Sarah here, Entier. You know Sarah very well. She's the main principal investigator of the QandA collaboration. Some of you also know our famous astronomer expert, Alain Klotz, who is professor at the Toulouse University and also working at the IRAP Institute in Toulouse. We have also Antoine Caillot. I don't know if Antoine is connected right now, but who is also our, let's say, amateur astronomer who help us a lot to give us some feedback about the tools we develop, what are the different needs of the community, etc., etc. So we no longer have Frédéric Carbin, who developed the website Kilonova-Catcher. His contract has finished, so he left the team now. So we also have a graphic designer, so Jennifer. And we have also a technical support for the website, the database. Everything is hosted at the IGC lab, which is a lab in Paris, near the CA, by the way. Okay. We have a new member in the team who will be devoted to public relation and to make a communication about the project, because none of these people have time to do this, unfortunately. So we will have Quentin André who will join us, and we work about 1 day per week on the project to help us to better communicate and give you also more information or quicker than what you have right now. So I hope that the next mail that you will receive will be sent by Quentin in the near future. Now we can move to funding updates for 2023. So it's always important for us to have some fundings to develop the project, and also to try to organize workshops or try to just update the current infrastructure we have. So last year we had what we call the CNRS MITI grant, and we had an extension of this grant for this year. This is about 10K euros, if I don't say wrong things. And as I told you also, we have a new collaborator for the communication and outreach, which is Quentin. Unfortunately, we try to have an ANR funding, which is a public funding for research, to hire a software engineer and to maybe organize a Kilonova-Catcher workshop face-to-face. But unfortunately, our project was unfortunately not selected. I tell you that just to be transparent and to give you all the information and details. And we are also waiting for an European proposal, the result of the European proposal for providing tools and new collaboration perspective for the whole European transient sky community. And for QandA, we can expect a few kilo euros from this proposal. So this is in the waiting process right now. So that's all for 2023. I will move to science in 2023, what has been done. So you have heard probably about the boat, the brightest of all time, gamma ray burst 221009A, for which the QandA collaboration and the Kilonova-Catcher group has made a lot of work. We received more than 200 images from all those people that I listed here. I hope I didn't forget anybody, because I would like to thank you all for this huge work and this huge amount of data. It took us some time to analyze all the data, because also this gamma burst was not in, let's say, good sky localization. It was really through the galactic plane, so it was complicated with a crowded star field, and also a huge extinction on the line of sight. But we managed to analyze the images and to produce a valuable scientific paper that is listed here. So once you will have the slides, and I guess you have the slides, you can click on this and you will have access to the publication. We are also in the process of submitting very soon a new publication to the MNR's journal. about an old follow-up campaign we organized with Grandma, the Ready for 04 #2 campaign, which was about following up swift gamma ray burst during the spring 2022. So I don't remember how many months we made the observation, but basically we got, if I remember well, 12 gamma ray bursts during this period. And again, we managed to analyze the data from all of those people, and they are part of the publication. And we will circulate the paper as soon as we have submitted it to the journal. So again, thank you for your efforts. It's a great pleasure to see that all this motivation and all this data of very good quality, by the way. We hope now to move to gravitational wave scientific papers, because in 1 month we will start with the gravitational wave 04 run, and it's going to be another story, but exciting story, I hope. I think I've finished on these 2 slides for the news. So we by the end of the last year and the beginning of this year, we released some documentation, tutorials, and let's say outreach documentation about the project. So you have on this YouTube link a public advertisement for joining the KNC program made by QandA and Louison. You are completely free to share this link to anybody who could be interested in it. It's like a 2-3 minutes presentation by QandA of the Kilonova-Catcher program and the gravitational wave astronomy we plan to do during 04. You have recently received the astronomer guide in an English and French version. I put the link, you can download the astronomer guide actually via the frequently asked questions section of the Kilonova-Catcher website. So if you click on this link, you will see that you will have access to the astronomer guide in an English French version. For Richard, who is here, I think I didn't forget to produce a Polish version of this astronomer guide. Just the graphic designer didn't have time right now to do it, but it's on our to-do list, so we will have also a Polish one. And finally, there is also a guide about giving news, general overview of the gravitational wave astronomy and the Kilonova-Catcher project. What are our goals? What are the scientific perspective for that you can download directly on the Grandma website, so at this URL above, or also I provided the link on this on our Kilonova-Catcher website, so you can download also the file here. So we have a frequently asked questions section in the KNC website, in case you didn't notice it. So I tried to post some stuff there related to questions you could have in your head. So don't hesitate to ask questions and to also request some contents to be posted there, so that we can enrich also the website with your feedback. Okay, I'm going to finish here for the news. There are some events. Unfortunately, I'm going to talk probably only for the French people, because I'm not aware about all the worldwide events for the astronomy outreach. But in France, in November, we will have the Explore Espace Festival at Montrouge. So again, it's close to Paris. Personally, I will be there for the SVOM mission, but I may try to also be there to distribute, to be there to talk with you about the Kilonova-Catcher program. Of course, you will find me, so we will be able to talk if you visit this festival at that time. There will be the French Astronomical Society workshop in Strasbourg in June. I'm not sure if I will be there, unfortunately. Sorry, Thierry. I don't know if people from QandA in the French side will be present at the SF2A workshop. They could tell you. But for those who plan to go there, maybe you will find some people of QandA there, so to talk about gravitational waves and Kilonova-Catcher project and other stuff you would like to talk with us. I don't see any other event where we could be face to face. I don't know if the French people who are here could enlarge this list. Of course, if you know in France, but in your country also some events you are organizing for outreach for whatever things, or you are participating, you really please don't hesitate to share these events by mail, via Slack, etc., so that everybody is aware of the different events that they could participate to. That I think could also bring some good motivation to everybody to see all those fancy events about astronomy. So I'm done here for the news. I don't know if you have any questions or if you would like to raise your hand for any topic. Oh, I don't. Sorry, I'm not looking at the chat. I don't know if someone is answering to the chat question. I see Sarah is answering. So I don't know if all the questions have been answered in the chat, and otherwise, if you have questions here, you can ask.
Yes, only Damien, to be sure not to misunderstand, for the SF2A workshop, in fact, there is 2 workshops on Friday afternoon. The one I am managing for the Pro-Am collaboration, but at the same time, on Friday afternoon, there is a multi-messager workshop. And I think it's there, Thomas Husneau
will be there.
Yes, I've just seen this afternoon that there is a poster given by Thomas Husneau for the QandA team. So I don't know, maybe there is 2 things in this line, SF2A workshop, the Pro-Am workshop and the multi-messenger workshop on Friday afternoon.
Yeah, so maybe there will be an overlap between the 2 sessions, but well, people will be there. So even if we are not in the Pro-Am session, don't hesitate to maybe to try to identify QandA people there and try to discuss with them if you would like to. Maybe we will give you the list of the QandA people who participate to the SF2A, so that you can also try to identify them there.
Yes, it would be
Yes.
nice. Okay.
Yeah, we have to make a list, and unfortunately I didn't have time to go to the SF2A this year. I was there the last year, but this year complicated. Okay, so we can move on, I think. Otherwise, yeah. Okay, so we can move on to the section number 2. The goal of this section here is to give you a rough overview of what is upcoming here with the O4 run gravitational waves, and what kind of targets we plan to observe altogether, QandA and Kilonova-Catcher. So I will start with a very brief reminder, but you know that we in QandA and also in Kilonova-Catcher, we are observing what we call the transient sky. And so we are trying to study very energetic and short time in comparison to the astronomical times events that are usually related to explosive or cataclysmic events. And those events can be studied via different astrophysical messenger. Of course, the light. Most of those events emit light in a broad range of wavelengths, from gamma rays, X-rays, up to radio light. Some of them emit particles, and some of them are expected to emit particles, high energy particles. And also some of them could be sources of gravitational waves, when masses are accelerated at compact masses are accelerated at high energy. We expect gravitational waves emitted in such a condition. So in our site for Kilonova-Catcher and QandA, we are going to study sources, transient sources that are going to emit light and gravitational waves together. Not at the same time necessarily, but they will emit both of these messengers. Probably maybe some of them will emit particles, but we won't go into this for the Kilonova-Catcher program right now. So just keep this in mind. We just observed two messengers related to the same astrophysical events. And so I wanted just to show you the Earth map where you can see the different gravitational wave observatories. So we are going to start with gravitational waves, and then we are going to move to electromagnetic counterparts. And so you can see on this Earth map that we will have for O4 four main gravitational wave observatories. The LIGO Hanford here, the LIGO Livingston detectors, so two detectors in the US. There will be one called Virgo in Europe, in Italy, and there will be another one called QandA in Japan. You will see that QandA will be very, very less sensitive than the three others detectors, but it will be running during the O4 time. We also have GEO 600, but it's a very small gravitational wave detectors and with a small, well, less sensitive than the kilometers scale gravitational wave detectors here. So the science operation will resume on May 24th. If I don't say wrong thing, you can correct me, Sarah, Michael, and others. For 1.5 years of operation, there will be two breaks. So this is what we call the O4 run. The O4 run will start on May 24 for 1.5 years. And there will be two breaks for commissioning, of period of 1 month each. So you can consider that the O4 run will be split in 3 periods of acquisition, 6 months, 6 months, and 6 months, separated by 2 commissioning breaks. I just also want to remind you that these gravitational wave detectors are able to detect gravitational wave source in real time, which means that there will be a short latency between the detection time and the release of the alert to the whole community, which means that we have to answer fast to the alerts because we will have the information very soon after the merger time. The main gravitational wave sources that can be associated with such a signal that will be detected by these 4 main gravitational wave observatories are those ones listed here by order of, let's say, probability of detecting them. Actually, you have more chance to detect mergers of binary black holes. We usually detect more binary neutron star mergers than neutron star black hole mergers, if I'm correct. And you could also be facing detection with not merger models, but with what we call burst models from core collapse supernovae. If you have a symmetric explosion of a core collapse supernovae, it can produce not the same kind of signal than mergers, but it can produce a gravitational wave signal. It is a very, very rare event, and we expect to detect such an event in the very local environment of the Milky Way. And I put other things because I'm not an expert of gravitational wave detection, so I expect that things could be discovered that were not expected. We will see during the O4 run. Okay, so this plots just to show you the diversity of the sources that are detected by the LIGO Virgo detectors since they are in operation in 2015. So in blue, you have all the black holes that have been, so black holes merging together and creating new black holes that have been detected by LIGO Virgo QandA detectors. In orange here, you have the neutron stars that have been detected, the merging neutron stars that have been detected by LIGO Virgo Cagra. And also you have here some orange and blue dots, which means that these are neutron star black hole merger candidates that have been detected also. And in green and in red, you have the neutron stars and the black holes that were previously detected previously to the gravitational wave detectors by indirect detection with electromagnetic signature typical of the gravitational wave influence of these black holes or neutron star to their close environment and typically to their accompanying stars. And you can see that since we have LIGO Virgo detectors, we have the population of black holes have been like multiplied by, I don't know what the number is, but the statistic is now coming compared to the previous epochs to the gravitational wave detectors. We have still a few neutron stars here compared to the ones detected in pure electromagnetic counterparts. And we expect the O4 to really bring the gravitational wave studies to population studies of black hole studies, and also, well, neutron star would not say that we do not expect to have such a population of neutron stars compared to the black holes, but we are going really to enter in population studies now.
Damien, I have a question.
Yes.
What is your x-axis?
There is no, it's just it's just a weird plot. Actually, there is no value here in the x-axis. This is just the way they decided to plot it things. This is not by epoch, by detection time, or by the masses are in the y-axis, but there is nothing in the x-axis. And if you actually go into the website developed by I think it's developed by LIGO Virgo. I can provide you the link. Actually, you can change the way they display things, and it's just graphical display where you don't have any x-axis here. Maybe
yes,
it's
because the monotonic shape of the curve concerning the neutron stars is amazing.
Yeah, but it's just the display style. It has nothing to do with physics or whatever. What has to do with physics is the y-axis. Like, for example, here you have a lighter black hole with a lighter black hole that will create a heavier black hole.
Thank you.
So this has sense, but y-axis, x-axis has no sense here.
Thanks.
This is what they call the diamond display. So just to give you also information about the typical distance at which we observe the different kind of merger events. And I will going to talk about the binary neutron stars and binary black hole merger events. These statistics are based on the last gravitational wave run that occurred on April 2020 to roughly April 2021. And so note that these sources are extragalactic sources. They are not in the Milky Way. They are extragalactic sources, and most, well, 50% of the sources binary neutron star merger are detected let's say around 150 megaparsec, 200. I have to recall you that we have very poor statistics here for binary neutron star merger. We have very, very few candidates for confirmed sources, I should say. For binary black hole mergers, we have more statistics, and this you have here the different distances. So binary black hole mergers are observed much farther away than the binary neutron star mergers. The distance horizon for the gravitational wave detectors is not the same for these two kind of events. For BNS, we were limited to, if I don't say wrong things, to 150 megaparsecs, 200 megaparsecs, something like that. Okay, so binary neutron star merger are very close, but you will see that the electromagnetic counterpart are faint. So this is the distance horizon we expect for binary neutron star mergers detection for the O4 run. You have here in the purple color for the different detectors. So for LIGO, we expect to reach almost 200 megaparsecs. This doesn't mean that we can't detect binary neutron star merger up to 200 megaparsecs, but this is the typical distance horizon we expect for these detectors. And for Virgo, Virgo will be still less sensitive than the LIGO ones during O4. And as you can see, for QAGRA, the distance horizon will be very, very close to us, like few megaparsecs at maximum. So we do not expect a 4 detectors detection in O4. If we have a 4 detection of the same events, this means that it's a very, 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 very interesting event. But don't expect to have 4 detections of binary neutron star mergers in the O4. At least 3 detectors would be awesome. Okay. So compared to O3, Virgo should double the distance horizon. So which is a good good news, because during O3 we were very limited by the sensitivity of Virgo. We were mostly relying on the 2 LIGOs detectors for having the a good localization. So 2 detectors, it's not amazing in terms of localization accuracy. So if you have 3 detectors, it's always better. So we expect to have better localization during O4. Actually, we will see, these are theoretical, let's say theoretical numbers. We will see what's the reality during the O4 run. And that's why the first months of the O4 run will be very interesting for all of us. And we'll go to the typical numbers you expect during the O4 run. For binary neutron star mergers, we expect to have 36 plus 49 minus 22 events during a year. It's just annual number, so during a year. As you can see, we expect much more binary black hole detections. And typically the number you can have in mind, if I don't say wrong things, it's like typically 1 detection per month for binary neutron star mergers. My colleagues could correct me. And for the binary black hole mergers, you could expect almost 1 detection per day. So it gives you the scales of detection rate between binary black holes and binary neutron star mergers. So you have all the numbers related to the median luminosity distance. I'm a bit surprised by this huge number of 400 megaparsecs, but we will see if this number is correct during the O4 run. And look at the sky area you expect for the localization of the sources are those ones. So we still expect to have large localization area for O4. Don't expect to have like 20 square degrees to cover only. We will probably have large several hundreds of square degrees to cover in the sky to cover the localization sky map of binary neutron star mergers. You note that also the orbitals are large. That's why we are going to see what's going to happen during the first months of O4. Do you have any questions about gravitational waves?
Yes, Damien, I have 1 question. This is
Yes,
Roger.
go for it.
Looking at the large distances that we expect for the future, does that mean that the optical counterpart will also be maybe fainter than before, will be harder for us to detect?
Exactly. The further you are, the fainter will be our targets. I will show you later what is the typical magnitude we expect at the maximum brightness for kilonova. And then, typically at 200 megaparsecs, you don't expect the source to be, let's say, brighter than 21.5, 21 magnitude in the R band. And of course, if you go further, you will be fainter. So we will probably, I don't know how, and also if you are further away, the detection for the gravitational wave detectors will be less significant. And so you expect larger error bars on the on the localization sky map. So we will see what are the different cuts we apply to send you the alerts, but there will be likely a cut on the, for example, credible area that we are not going to send you like a 10,000 square degrees sky maps, because it's like just probably a waste of time. But I'm saying that right now, but this is my personal opinion. But we will see in QandA what are the different cuts we will apply, so that you will have a chance to detect something.
Very good. I will prepare my budget for a larger instrument.
Yes. Even for us, it would be complicated. For everybody, it would be complicated at 200 megaparsecs and above.
Okay, thank you.
But we will try. So if there is no other questions, I can move to the electromagnetic counterpart. So this is what you are interested in normally, but maybe I guess you are interested in gravitational wave studies also. And so I will go through the astronomer guide we sent you a few weeks ago, and we will try to see what's inside, and also what are the typical information you can find. And typically the questions you could have in mind are those followings: what are the interesting gravitational wave sources for us? What kind of information QandA is going to send to you for observing those sources? Also, how fast should I observe a gravitational wave alert once I receive the alerts? And how fast should I to send my images also? What are the expected electromagnetic counterparts? Plenty of questions. And I guess you will have plenty of other questions also in addition to those ones. But we will try to at least answer those ones through the slides that are coming. So these are the first 2 pages of the astronomer guide. Is just to give you the typical astrophysical scenario we expect to give you as an alert of gravitational wave. So we are going to focus on binary neutron star mergers. I will tell you, well, I can tell you right now why. This is because this is the astrophysical scenario that will provide the better chances of having electromagnetic counterparts, because you can start with 2 neutron stars that are orbiting each other, losing part of their orbital energy into gravitational waves, so getting closer and closer, that at such a point they merge together, and a fraction of this of the matter of the 2 neutron star will be expulsed in the blast wave, actually in the interstellar medium. So the time at which the 2 neutron stars merge is called the T0. Let's say we will call it the T0 time. This is the time where the gravitational wave signal is the strongest, and you can easily identify it with the gravitational wave detectors. Well, easily. It's speaking like this, it seems to be easy, but it's not that easy. Following the merger of the 2 neutron stars, so as I said, as I told you, you have matter that is expulsed to the interstellar medium in some cases, but this is what we observed during the famous August 2017 event. You can observe what we call the gamma ray burst, which is the jet of plasma that is also expulsed in the interstellar medium, but at very, very, very high velocities, very close to the speed of light, like 0.999 the fraction of the speed of light. That's why this emission is highly collimated. This is just due to the beaming effect of the ultra-relativistic motion. And so, as you can understand, you have 2 types at this stage of, let's say 2 types. We have 2 kind of ejecta. So someone which is going to be related to the future kilonova and this gamma ray burst jet here. Actually, the kilonova emission can be split into, let's say, 2 different kind of ejecta. you have an ejecta that is going to be expelled through a torus of plasma, let's say, that is expanding outwards through the equatorial planes of the orbital motion. And so this ejecta is supposed to be very rich in neutrons and will produce inside this ejecta heavy elements. And those heavy elements, so this is gold, this is strontium, this is uranium, this is all these very, very heavy elements of the Mendeleev periodical table. And all those heavy elements are highly efficient in absorbing bluish light. So this kind of kilonova ejecta will appear redder because the blue light is absorbed by the heavy elements that are synthesized inside this ejecta. And you have another kind of kilonova ejecta that is moving faster than these ones along the pole of this along this axis, the polar axis, let's say. This is not collimated as the gamma ray burst because the motion is less relativistic. So you can see something like a bubble moving more or less in the polar direction. And here inside you have less synthesis of heavy elements. And so this ejecta is called, well, it's a characterized lanthanide free. Lanthanide are the name we give to these heavy elements. And because you have few heavy elements in this ejecta, fast ejecta, you will see this kilonova component as a blue component, at least blue, much bluer than this equatorial radial kilonova ejecta. So you have one ejecta which is rich in heavy elements and another one which is almost free of these heavy elements. And so this is very important to keep this in mind because it's going to drive our follow-up strategy of such events, because we will need to characterize the both components and the color evolutions of the overall kilonova that will move from blue color to red colors. I will show you this later. So this is written, all this information are written here in this text. You can have time to read this text later. I will move to just something to note, in case we are lucky or unlucky, depending on your point of view, in case we are looking directly into the direction of the jet, note that the light coming from the jet will be much, much, much brighter than the light coming from the kilonova components here. So usually we are happy if we detect sources, these gravitational wave gamma ray burst sources, slightly, or let's say slightly off axis, so that we can still detect some light coming from the jet, so that we can detect also the gamma ray burst with the satellites, but we can clearly detect also the kilonova counterpart. Otherwise, we won't see anything from the kilonova, we would see only the jet light. Okay. So I was talking about this August 2017 Gravitage famous events. You have heard about it in many ways, I guess. Just a brief reminder of what this kind of events brings to the science. The first plot I show you on the left part here is the detection. So you have here this green banana shapes. Here are the detection provided by the gravitational wave detectors. That is also cross-match with a positive match, sorry, with the localization area given by the Fermi GBM satellites, which is a gamma ray instrumented satellite. And actually, the Fermi GBM satellites detected this jet light, but we were seeing this jet light slightly off axis. So it allowed us to detect 10 hours after the gravitational wave signal this point of light here that you can see in this image is taken by the SWOP telescope. You can see here there is nothing 20 days before, and there is something here 10 hours after the GW trigger time. You can see also here an animation of the different epochs of detection of this kilonova counterpart. And what is interesting is to note, so as I told you, there are two components for these events, a blue component coming from the polar kilonova, let's say, and the red component coming from the ejecta that is composed with a lot of heavy elements. And I just show you this animation just to tell you, to show you in real time if it works. So we are days before. Oops, sorry, I put in pause. We are days before. So you can see here, you will detect something very blue, as you can see. So here you have the spectra that are been taken in also in different at different epochs. You can see that the point here is going to be redder and redder as long as the time is passing, and I will tell you why after. This is going to become redder and redder, as you can. I will just show you again once if I can. Yep. So you can see again at the beginning we are very blue, the kilonova is very blue, the spectrum is peaking at very blue wavelengths. So blue is here, red is here on the right part of the spectrum, and then becomes very red. So this is the typical scenario we observe for this kilonova, the only kilonova counterpart associated with the gravitational wave events. It was actually a case very, how can I say it? A very expected, which is something not expected in science, but we were very happy to see this event at that point. This is the scenario that has been imagined to explain the blue to red flux evolution of the kilonova. This is exactly what I told you before. You have the GRB jet here. You have also a blue kilonova evolving along the jet axis, not collimated as the jet, but still evolving along this polar axis. And you have this red kilonova evolving at less speed than the blue kilonova, but composed of much larger fraction of heavy elements than the blue kilonova. And for this August 2017 events, we were observing roughly at such an angle compared to the jet axis of the event. So the two neutron stars are merging and the jet is launched through the polar axis. And these are spectra that has been made of the kilonova counterparts at different epochs, and people were able to identify strontium absorption, broad absorption in the spectrum of this kilonova, which enable us to identify for the first time heavy elements produced in such explosive cataclysmic events. This is the first direct evidence that these heavy elements produced, which means that a very neutron-rich explosion has occurred here. So it was also a way for us to validate the astrophysical scenario that neutron star contains a lot of neutrons. They are very compact, and when they merge together, they can produce the physical condition to synthesize heavy nuclei. So it's a very direct evidence of such a process, what we call R process for nucleosynthesis of heavy elements. So this is a golden event. So we hope to have another golden event during 04, and we hope you to detect this guy, and so that to produce all this science then, thanks to your detections and to the way we will have to trigger spectroscopic observation also based on the localization you will be able to provide thanks to the detection. I stop here for questions. If you have any questions related to gravitational wave astronomy, binary neutron star mergers, kilonova, if you would like to have questions. If these are questions related to follow-up strategy, what we expect, etc., I will go through the slides just after. So probably I would answer after. But if these are related to a general context, you can feel free to ask questions.
I'm Richard. I have a question about maybe a notice. About slide number 19, what are the interesting gravitational wave sources for us? Not this one, which is, could you move to the slide? Not what are the next one? The next one.
Yep.
Okay, this one. Here there is the point number 3, and you the one sentence here is not correct from my point of view. I mean, this first sentence: the plasma jet traveling at the speed of light is launched. From my point of view, I think it should be written in a way that the light is traveling at the speed of light, but
yeah,
particles are moving near this. It is kind of style, but I've translated it to my native language, and it was my some notice, some one notice.
So you're right about this. There is a bit of mistake actually. The plasma jet here is not traveling at the speed of light, but it's traveling very, very close to the speed of light, like 0.999 the fraction of the speed of light. But this is not the speed of light. So yes, there is maybe an incorrect information here.
A little style correct only, but
yep.
Everything in the astronomer's guide, for me, it's very good.
Thank you. And why I didn't talk about binary black hole mergers is just that except in exceptional conditions where matters could be around the two black holes, but a black hole plus a black hole equal a black hole with no light. let's say it's as simply as this, but except if you have matters around that could be reaccelerated or accreted by the merging black holes, you do not expect any electromagnetic counterpart. And if you have such electromagnetic counterpart, the problem is that binary black hole mergers are detected very, very far away. So probably the electromagnetic counterpart would be very, very, very faint. And for neutron star black hole mergers, we will probably send also alerts from star black hole mergers. We will have very few of them. And depending on how the neutron star is actually merging with the black hole, you will expect no matter ejected in the surrounding medium, or you would expect a few fraction of the neutron star matter that is expulsed into the interstellar medium, depending on the way the neutron star and the black hole are merging. So this is a completely uncertain scenario for electromagnetic counterparts. For binary neutron star mergers, we are pretty sure that we will have all the time at least matter that is expulsed into the interstellar medium, and a way to have then radiation from this ejecta. That's why we focus on binary neutron stars mergers. So I will go through the section 3 because it's already 1 hour of meeting. If you are not tired, I will continue, and I will give you the information about the follow-up strategy for 4. I will try to be as fast as I can. First, what you have to note is that gravitational wave events are poorly localized events. So unfortunately, we relied on few gravitational wave detectors, and the way of detecting gravitational waves is not the same way that we detect stars with our optical telescopes. And this is the typical, let's say, localization area we got during the 03. It was the 03, no, of 02, right? It was the 02 run. Okay, for such events. So you can see here that what we call the 90% contour here is the chance probability of having the gravitational wave events within this contour. So we also usually plot the 15% contour, so 50% of chance to have this gravitational wave event, but usually we rely on this 90% contour. You can see that for this event, the contour was almost 1,000 square degrees. And what you also have to notice, so maybe you are not familiar with such a sky projections here. It's an all sky projection, but what you have to note here is that the gravitational wave events can be spread, the localization can be spread into the both hemispheres. So there are chances to everybody to detect actually the electromagnetic counterpart, because we barely don't know where is the gravitational wave events. We hope that during the O4 run, the localization will be much better so that we will have less part of the sky to scan. But this is not sure at all. We will see what the O4 run will give us actually. And so having this in mind, you could ask yourself the question where to search. So the where to search is the question that the QandA collaboration tried to answer with a very custom software that will actually look at the different portion of the gravitational wave sky maps and compute the probability based on the population, for example, of the galaxies that you have in such a part of the gravitational wave sky map, or just based on the probability of having the gravitational wave events that is provided actually by the LIGO Virgo detectors. We are going to compute optimized pointing strategy to pave, actually to scan in a smart way, or in a smarter way, the gravitational wave localization region. For most of you, you have small field of view telescopes, if I'm correct. Let's say less than 1 square degree field of view, like 1 by 1 degree. I think there are few people who have such a facility. And so for most of the people, the way we are going to produce observation plan is just to look at the galaxies that are inside each tile we are going to cut based on the field of view of your telescope. We are going to pave the gravitational wave sky map and see where are the most probable region that could host the gravitational wave events in this sky map. And these are based on the potential host galaxies that could actually host the gravitational wave events. And so typically the sky map we are going to provide you is such a sky map where you will find some typical information related to your observatory localization information, and also the time since the trigger time. So the T0, remember, this is the merger time, so the time at which the two neutrons have merged. You will be able also here to visualize the galactic plane along the celestial sky here. We will provide you also in yellow the 90% contour of the gravitational wave localization area. And you will have in red here all the pointings. So it will be the center of your image, these pointings that we schedule for you. And we think that they are the optimized pointing to find with your setup to detect the Kilonova counterpart, or actually to have a chance to have the gravitational wave event in your image. Maybe you won't be able to detect it because it's too far away, or because you have clouds, etc., etc. So it depends on the conditions. And this kind of blue-purple region here is the region that should be visible for your observatory. So this would be your visible sky. At the time you choose, you are able to choose the time from T0 to T0 plus a day with a bin of 1 hour. And this is the visible sky with a 30 degrees of elevation above your horizon. So note that these observation plans are produced by the QandA code. So we are going to produce in the same way the observation plan for our professional telescope than we are going to planify your observation plan for your telescope. So we are going we are using exactly the same code for pro and amateur telescopes for the scheduling of the observations. What kind of sources you have to search in terms of at optical wavelengths? So this is the light curve of ATGFO 2017 Kilonova candidates, the only one we detected in August 2017 years. You can see here, so you have the time since the merger time here in days, and you have here the apparent magnitude. And the different bands are given here from the UV in the dark blue color to the infrared in the darker red colors. So your filters are more around G to, let's say, up to IZ for those who can have Z. And what we observe, as I told you, we observe different flux evolution between the blue band and the red band. This is because these are just different ejecta that evolves with different dynamics. And so the blue ejecta evolving, so launch in the polar direction, in the gamma burst jet axis direction, is evolving, actually fading very fast. As you can see, in several days, we have lost several magnitudes. And so that's why we have to be fast, because these bluish color are going to fade very, very quickly. In the redder bands, the evolution can be very different for this kilonova. You can see that we have even a kind of plateau in the infrared, wavelengths of the emission of the kilonova, so that we can observe it for a longer time. And so typically we expect a very fast rising time of the optical emission. So when SWOP detected 10 hours ago, 10 hours after the gravitational wave mergers of GW 170817, it was, the kilonova was almost at the peak of the brightness, actually. And then it is, as I told you, followed by a fast fading behavior of the optical and the infrared emission. Typically more than 0.3 magnitude per day is the typical mag rate you expect in the very few days. So for us, the kilonova counterpart, based on our sensitivity and the typical sensitivity you have with your telescope, will be, the time window will be for being able to detect such a kilonova will be, I would say, about 2 or 3 days. Even 3 days, maybe it would be complicated. But of course, it depends on the distance of the event. And the gravitational wave detectors, they provide us the distance of the event in the alert information. And that's why also, because we have a strong color evolution from blue to red bands, that's why we always ask you to try to observe in 2 filters at least, a bluish filter and a reddish filter, and to try to have consecutive successive observation in the bluish filter and then in the reddish filter, and so that we are able to assess if the transient candidate you detect is behaving in such a way that is probably a kilonova candidate. The absolute magnitude at the maximum brightness, so at the peak of the kilonova emission, is expected to be around the minus 16. So in terms of apparent magnitude, if you replace this absolute magnitude into apparent magnitude at 100 megaparsec, for example, you will have a peak of the magnitude at magnitude 19. At 200 megaparsecs, it would be 21. So for the 40 megaparsec event of August 2017, we had the peak magnitude at around 17, if I remember well. And so depending on the distance, you will have to also expose longer or stack more images to reach such apparent magnitude. Okay, I think you got the message about this. Do you have any questions about this kind of things? So the follow-up strategy is actually detailed in this page I show here in the top right of the slide. I think I have one slide to just talk about it again. If you have any questions, feel free to ask about this. Or can I move forward? because it's going to be late. I didn't have a look at the chat. Eric, you ask, since the transient is expected to be faint, is it better to observe unfiltered until it is found? Actually, we have a long-term debate about unfiltered and filtered observations. At the beginning of the project, we were asking people to start with unfiltered observations so that you can go deeper and detect the transient, and then we will move to color observations once we have identified that the transient is the good one. But from my perspective, and I don't know if my colleagues are still connected, but we are now moving more than in directly observing in color filters, because if you use unfiltered observation, well, we can assume that these corresponds to R-band filters, and then we could make a color, let's say, analysis of the light curve afterwards with such an unfiltered point. But we would prefer that we start with filtered observation to be able also to identify better the transient, because these kilonova are a very specific color evolution. So having such a color indication is very important in identifying, in disentangling between supernova, between cataclysmic variables, between other kind of optical transients. And so we prefer that you start directly with colored filters. You can expose longer, or you can stack more, maybe to reach the same sensitivity that you would have reached with a shorter exposure with unfiltered bands. But yes, we preferentially also prefer slow and filters with narrow wavelengths passband, because we really need to be able to say if the transient is blue or red. And we also, when we will emit circulars, we will tell to the scientific community that we have detected something that is very blue, and we have to provide a color index of such transient. So it is very helpful to have such a color information, and in Sloan or in Johnson cousin filters if you don't have Sloan, because some of you don't have. Of course, if you don't have any color filters and you can just observe in unfiltered mode, you just go for unfiltered mode, it's okay. But if you have colored filters, use them. This is my message, I would say. I will move to the last thing I wanted to show you tonight. This is about the working organization during O4 and the typical timeline you may expect from the merger time, the alert provided by LIGO Virgo, the grandma generation of observation plan, etc., up to your observations. So I will try to explain you this in this simple timeline. Keep in mind that all the latencies that I will show you here are orders of magnitude. These are not accurate numbers, but these are, I would say, accurate orders of magnitude of the latencies we expect for the different steps. So we start at T0. You have your two neutron star mergers that are merging. You have the GW merger time here. So LIGO, Virgo, Cagra detectors are able to detect such a source in real time. They have people in shift, actually, scientists in shift, and they have also automated alert process that are able to send in short latencies preliminary alerts of such events. Typically, in very few minutes, we will have the very first alert related to these binary neutron star mergers. We call this time I call this time, this is my own scale, the white scale, the time of LVK, LIGO, Virgo, Cagra, the time at which the LVK collaboration provides us first information about a merger of binary neutron stars. In the same time, so GrandMA is listening to the alerts sent by the LIGO Virgo CAGRA collaboration through, for those who are familiar with such a system, through the Global Coordinates Network Notices system, which is a system that allows all the observers to process in real time the alerts provided by any collaboration. And this will take a second to process this alert and to distribute it to GrandMA and to QandA via alert notification. I will show you how we are going to notify you about this alert, but just keep in mind that it takes a second for us to process the LVK alert. Then, once we got the alert, we have the localization sky map of the event. We have to process observation plans for you. And so this is done inside the GrandMA network, the GrandMA software architecture that is going to also produce the observation plan for the Pro telescopes. And this can take several minutes, up to 10 to 20 minutes, depending on the number of telescopes that will have an observation plan. We do not plan to produce observation plan for the telescope that won't be ever able to cover the GW localization region. So just keep in mind that it's going to take 10 to 20 minutes. So we will be around 30 minutes after the merger time, so the physical time, let's say, and we will be 10 to 20 minutes after the first alert has been released by LVK. I suspect that it's going to take 1 to 5 minutes. It's actually, well, no, more than 1 to 10 minutes to distribute all the observ. Actually, it's fast. It's not that time, but it's pretty fast. It's going to take 5 minutes to distribute the observation plan to all of you. By observation plans, I will show you what it looks like, but it's also producing the sky map I showed you before, and putting all the information into the QandA website also. So we will be 35 minutes after the merger time. And so theoretically speaking, at this time, you should be able to start your observation. You will have the list of the pointings you have to do, and then you can start. But I suspect that we will have latency the time that you get the file. It can be an hour, it can be more for others that don't have time to observe because they have other things to do, more interesting. Even if we hope that you will find gravitational wave sources more interesting than other things. But we expect that you have short, very fast response to those alerts, and you are able to observe as soon as you can those pointings that GrandMA will provide to you. So let's say that an hour after the gravitational wave merger, we can start observations. And then we are going to go through the different pointings, adopting the follow-up strategy for each pointing with a successive exposure in the blue band and in the red band, and then moving to another target, blue-red, another target, blue-red, etc., etc. Note that during this process, there could be updates from LVK, so that will provide an update of the localization sky map of the event. There could be also a retraction that, okay, this is not a real event. Sorry, guys, we retract the events. And so we will warn you that the event is a fake event so that you don't spend time in for nothing in observing. Once you will have we will have an update from LVK, we will also try to reprocess an observation plan that is optimized to the new localization region we have. So you might be also be prepared to have a new observation plans, typically a few hours after the first one, or well, I would say hours after the first one. It can happen. Okay, the typical information we are going to send to you via the GrandMA alert. So actually, we are going to get the LIGO Virgo CAGRA alerts, and we are going to reprocess them in the GrandMA way to distribute them to the Pro and AM amateur telescope. And the information you will have are typically the astrophysical origin of the gravitational event. Is it a binary neutron star merger? It is a neutron star black hole merger. It is black hole binary merger. usually you won't receive BBH events because we won't send them to you because they are almost nothing to do with such events for electromagnetic counterparts. You will get also the probability that at least one neutron star was involved in the binary compact object merger. So of course, if it's a BNS, you will have 100% here. But if it's a neutron star black hole, sometimes we have a blur region of masses where we don't know if the source is a neutron star or a very light black hole. So this probability can be interesting in knowing if a neutron star if a neutron star black hole system is hosting a neutron star actually. And you will also get the probability that matter has been ejected after the binary compact object merger. This is important for the electromagnetic radiation afterwards. You will have the distance of the event in megaparsecs. You have the expected R magnitude of a kilonova that looks like the 2017 kilonova that we detected a few years ago. Look at it at the distance that is provided by the LIGO-Virgo-Cagra collaboration at its maximum brightness. So typically what we are going to give you is the magnitude here at the peak, at the distance of the event. And you will have the names of the gravitational wave detectors that are involved in the event detection so that you will be able to see if there are only one detector, 2 detectors, 3 detectors, maybe 4 detectors. No, keep in mind that the more detectors you have in the detection process, the better will be the localization. You will have also the estimated date in UTC of the merger. It helps you to give the context of the time of the merger, and a scale that is called the scientific interest of following up the event. On a scale ranging from 0 to 5, this is based on the code that we have to update, by the way, and that is going to rate for you to give you a very clear idea of if the event is a golden event or, let's say, a regular event. And for example, here for this event, you have all this information that I just described above. You can see that here the degree of interest for this event is pretty low. You can go for it if you want, but note that if you have something that is very high, like let's say above 3, it's something that worth to try, really. How you are going to be notified? So we will have 3 channels to give you the information about the alerts and the observation plans. You will have the Slack channel here. You will have a dedicated Slack channel. Actually, we are already testing alerts that are imported from QandA. This is called right now test Sky Portal. Sky Portal is the software, the web interface we use for QandA Pro collaboration to manage all the alerts and the data we collect. And so Sky Portal is forwarding us the gravitational wave alerts. So if you look at this test Sky Portal channel in our Slack, you will be able to see the test gravitational wave alerts that we receive every day, by the way. For cut, we put for binary neutron star merger only and 200 megaparsecs, I think, in terms of distance horizon. This is what I put as a limit for now. It can be changed at any time. So this is already working. In the near future, I will change test Sky Portal by gravitational wave alert. It would be more straightforward for you to identify what is the channel to get the alert on Slack. Of course, you will have the information of the alert on the Kilonova-Catcher website. And also you could click here to get your observation plan. So it's going to download for you a CSV file if you click on this with all the pointings. And for those who who agreed in receiving their observation plan by mail, we will send by mail the observation plans. And the observation plans look like this. You have different tiles, so different pointings to do here. So they are listed here. And you have the coordinates of the center of the pointing you have to do. In right ascension degree, it's degree here. It's hour, minute, seconds here in right ascension. Then it's declination in degrees here, declination in degree, minute, seconds here. And here you have the probability for you the probability that this tile actually contains the gravitational wave events. So don't be afraid if the number is low. In case of a large gravitational wave localization error, it's normal that you get a low probability to get the events. So don't tell to yourself, oh no, this is very few, there are very few, this is highly unlikely that I'm going to detect the gravitational wave event is not in my tile, I'm not going to observe. Actually, if we have very good localization area, this probability will be huge actually. Well, huge, not exceeding 1, of course. And all the tiles here are ordered by this probability. So we suggest you to start with the first pointing because this is the pointing for which the probability that the gravitational wave event is inside your tile, your observation, is the highest among all the different tiles here. Don't forget the follow-up strategy. So just a very, very quick reminder. We expect to potentially have a blue kilonova counterpart that is visible from 1 to 2 days in the bluer band. It's fading very fast. And we also expect to have a reddish kilonova that is visible from 5 to 8 days, but I would say more from 2 to 3 days, let's say. But which is evolving less fast than the blue one, but still, it's still a fast fading behavior. It's much faster than the supernova. And so in the astronomer guide, we provide here 5 steps for you to try to get your own idea of how you are going to proceed for the observation. And as I told you before, what we expect from you in the best case, if you have the filters, is to start with the blue filter. You can make 30 seconds of exposure, several 30 seconds of exposure, well, 30 seconds, 300 seconds, sorry, of exposure. But I mean, it depends on your setup. You know better than us your setup and how long should be your exposure to reach such an apparent magnitude. So, but what we expect from you is that you are going to send images with 2 colors for the same tiles that you observe, one in the blue color, one in the red. If you can't, send preferentially a red image. If you can't have filter at all, just send unfiltered images, and that's all. Of course, we prefer color. Expose as long as it is needed to detect the kilonova, giving the apparent magnitude of the peak of the brightness. So if it's 17th magnitude, it's not going to be the same exposure time than if it's a 19th magnitude, of course. We also ask you to observe several sky regions, so several pointings of, we don't ask you to do all the pointings of these observation plans. Probably you will have too many tiles to cover, but at least to do several of them would be very, very good to have a large coverage of the gravitational wave sky map. Also, what we request, so this is not, we don't ask you, we more requests to send calibrated images. By calibrated, I mean dark and flat corrected images, at least dark corrected images. If you can do it, astrometrically solved images also, if possible. I know that some of you are able to do this. I also provided several times a link to astrometry.net website if you want to use it for making the astrometry. It works very well to do such a thing. And so this is our request for you to, before you send your images to us, to be sure that you have calibrated images. And also, again, think about making revisits. So once you have detected, well, observed a given tiles, so you can go to the other tiles. But at some point, it would be good also to come back to the first tiles you've made so that we are able to assess if the source is fading as we expect for kilonova, and also to check the color evolution of the fading flux. So this is also important to make a revisit in the same night. If you don't have so much time during your night, maybe you could prefer to do only 1, 2, 3 targets and revisit them several times. It's up to you. We will refine this strategy, of course, as long as we are going through the offer run, but I would say that revisits are also a very important thing to keep in mind. I won't go into the detail of how to send your images. I think the astronomer guide is well detailed. For this, I will let you read this, but I will just wanted to emphasize to highlight the basic rules we ask for you for the files you are going to send to us. I remind you that we only accept fits, so .fits or .fit file. These are the only files we are going to manage. We ask you to be very careful about the name of your image and especially about the rules here to avoid the special characters that prevent us from doing automatic processing because there are some space in the name that make the code bugging or something like that. So it would be great that you really have a look at these rules here. And so you have mandatory information to provide in your feed header. These are very basic information about the coordinates of the center of your image, the time at which the observation started, the time at which the observation ended, the name of the filter you used. If you make stacking images, it would be great for us to get the time at the start of the observation and the time at the end of the stacking epoch, I would say, so that we can compute a mid time that is compatible with the whole period of observation you've made. And finally, I have to tell you that you can send here in this drop and drag function to send your images, or also if you click here, you are able to send several images at once, but not in zip or tar archives. I know that this is painful a bit for you, but we are still not able to just dezip. Actually, we just recognize only fits files. So if you provide a zip file, it will be rejected. So you will be able to send, I think the limit is 10 images at once. So at least it is, in case it is okay. We have prepared in the last part of the astronomer guide some good ways so that you can be well prepared for the observations and also to be well prepared once you receive an alert and an observation plan. I will let you read this kind of advices, and don't hesitate to ask us questions if you are completely lost. My message is that if you are lost in the process of all of this, don't panic. And also don't get stuck. So if you have a question that you don't know what to do, you don't know where are the informations, etc., you don't know how to connect to the website, etc., please contact me directly. I will try to respond as fast as I can. I know that sometimes I don't respond very fast and sometimes I forget to answer you. I apologize for this, but I will try to respond as fast as I can. So you have my mail here and you have my name in Slack. So I think there are 2 Damien Turpin on Slack. So just contact the CAA one. Of course, if you have questions related to the observations strategy you plan to do or how to send the images you don't remember, you can ask the whole community, of course, via Slack. We had Denis and Roger were discussing at the beginning of this meeting about how they were going to observe what would be their exposure. That's good discussion. Don't hesitate to have such a discussion on Slack or in other channels you have. That's good way also for everybody to have this information. And also, I hope that we will be able to provide you valuable information in our frequently asked questions section in the Kilonova-Catcher website. For those who are not in our Slack, who didn't join yet our Slack, you have here a link. You click on this link and you will be invited as a member, a new member for our Slack. I think I will finish on this last slide. I'm sorry, it's a bit long, but I wanted to give you all those informations, and you will be able to replay this meeting again so that you will be able to catch the information you may have lost afterwards. Upcoming task to do for all of us for May, because the O4 is coming very soon. For me, I have a lot of things to do, I have to be honest. But some of you asked me if I could provide test alerts to help you to train yourself in using the different communication channels, to understand the different information you are going to have, the observation plan you are going to receive to test the system. I have to do this. I'm going to do this during May, just before. So maybe at the beginning of fall, we will be partially ready, but I will try to do my best to do this, to send you these alerts. The test alert, as I told you before, they are already available on Slack through the test Sky portal channel here. If you click on some links, you will be redirected to some website where you have no rights to access. I'm sorry, I have to change also the content here of that is displayed on the alert. This is something that I have to do. I have to push also an update of the Kilonova-Catcher website. This is still not the last version of the website, even if it's not going to change so much for you. But for us, it's better because we have to put all the logo of the partners, etc., and correct few the display bugs. So I hope to do this before 4. And this also relies on the IGC Lab technical support. And also, I deeply apologize for those who are waiting the feedback for their images about the great GRB 221009A, and those who provided images during the spring GRB campaign 2022. I have to give you my feedback. I'm sorry, I'm so late. I have so many things to do, so it's always on my to-do list. I promise that I am thinking of this all the day, but sometimes I don't find the time to do it properly. I already make one for Mike Freeberg, I think. So I will try to give the same way for the feedback. And for you, of course, you can look already at the GW Alert Slack messages that will be reformatted and also provided in another channel very soon, but you can go to the Test Sky portal channel and see what's happening. You can also look at the GW alerts we will provide in the Kilonova-Catcher website once I will be able to inject test alerts. Typically, these kind of things, you will have to be able to test the system, to join follow-up campaign, etc. Look at the schedule observation plan we provided to you, if they are consistent with what you expect, what you are capable of doing, etc., etc. And also read this astronomer guide and all the documentation we provided in the slide at the beginning. I show you the different documentation and video provided by also QandA to present the Kilonova-Catcher program, to prepare yourself and to have all the information in your head so that you are ready for having exciting moments and very exciting adventure to come with the O4 run. It's going to be a real adventure, I think, for all of us. I'm sorry, I've been very long. If you have any questions, yep.
Yes, hello, Damien. I have a question. When we receive an alert, if I understand, we have 1 hour to go to make the observation.
Well, yes, maybe this one is confusing. Actually, once you receive the observation plan and you get the CSV file here, you can go for it. I just assumed that we were probably the minimum latency we would have. I just assumed that it would be 1 hour, but maybe some of you would be very fast and would be able to observe as soon as they can, maybe several tens of minutes after the merger time. Of course, this is on best effort basis. So if you have no time this night because you are busy for other things, well, it's okay. Or if you can't observe because there are clouds and or the mood is too bright, or you prefer to observe another night following the 2 or 3 nights after the GW time, it's okay. The best for us is a fast answer. So
yes.
yeah,
Fast.
the fastest is
Okay.
the best for us.
Okay.
Because
Okay.
time is running out and the light curve is fading very, very quickly. As you can
Yes.
see here, it's fading very quickly.
Yes, okay. I understand. Thank you.
Yeah, Damien.
Yep.
I was wondering, so when we send the images from each pointing location, do you guys compare them to some sky map then to see if there's an optical counterpart in there?
Yes. So once you are going to provide an image related to a pointing here, so on real time, I hope it's going to be on real time, but it will be very, we will be on, because we will have scientists on shift. So we will have people that will look at the images all the time. And so once we get new images in the folder, we will look at the images and try to find, we have detection software to find optical transient inside and get the photometric results also and also once we have the photometric results from your image, we can combine them with QandA data so that we can, have a better sampling of the light curve and also a better view of the flux evolution of the transient candidate you detected.
Okay, thank you.
We've been slow for JRB 221009A because well, it's been a hard work, this gamma burst campaign and follow-up, and we also go through personal issue inside the QandA collaboration, so it has been painful for us, but we will try to be as fast as we can, because our goal also is that once we detect and identify something very interesting, we are going to send the new alerts through the Kilonova-Catcher website and also probably by mail. But here, just highlighting the coordinates of the candidates you find, if we think that it is a very interesting one. Because of course, if we have identified a very interesting one, we are going to stop tiling the gravitational wave sky maps. We are going to focus on the candidates then.
Okay, sounds good. Thank you.
I don't, sorry, I can't see the chat, so.
Damien?
Oui.
Yes. You confirm it's possible to have an example of the observation plan, because I want to make a program which will be able to transform the observation plan to a script which will be able with that program to be able to make an automatic observation with our remote telescope.
Yes, I can provide this right now. I can provide it. I can provide the CSV file we are going to send to you during 04. Normally the format should not change, so it's fixed now. So yes, I can send this to you. I will take this action.
Yes, I will be very interested by that.
Even if it's not, well, I mean, I will send you an observation plan that probably has been made for another telescope for random targets, but it's going to be what you are interested in is the format, right?
Yes,
and
just
also,
yes,
and also the content of an example of the content. Yeah,
yeah.
okay. I'll do this. Yes.
Thank you.
Yep. Any other questions related to all the topics we've discussed? Maybe.
Yes. Excuse me. What is the difference about a black hole issue of one star alone and black holes issue of majors?
So you mean what would be the different scenario between having a black hole merger and a black hole neutron star merger?
Yes.
Yeah.
Yeah.
I have a video and the slides on another
Yes.
presentation. I could add them into this presentation later, But well, I'm not a specialist of this, so you have to. So I don't know if my colleagues are still there, but I can give you the answer. I think that is correct. So actually, the difference. So if it's a black hole merger, you have no matter around, you just have black hole. So light comes from particles that are accelerated and we emit lights to cool down actually. So if you don't have any matter, if you don't have any particles to accelerate, you won't see any light. And typically, if you have two black holes, well, you have with no matter surrounding them, they would just collide, emit gravitational waves, but there is no matter to accelerate and to expulse into the interstellar medium. So you do not expect any electromagnetic counterpart because you have no matter for this case. For the neutron star and black hole mergers, so you have matter that is in this neutron star, but to be able to see radiations, post-merger radiations, you need matter to be expulsed in the interstellar medium so that the matter can be accreted on the newborn black holes and then re-emitted, re-ejected, re-accelerated so that it can emit light. So you have to destroy the neutron star in such a way that fraction of this matter is going to be expelled. And this highly depends on the way the neutron star is colliding with the black hole. If the neutron star is falling directly into the black hole will not have time to disrupt the neutron star through tidal forces. And so the neutron star will just jump directly into the black hole and you have no matter that is expelled and you just have a heavier black hole at the end. So here in this scenario, you won't have light. If the neutron star is not falling directly into the black hole, but I don't know, making a kind of tangential movement, I don't know how to say it, then the tidal force will be able to disrupt a fraction of the neutron star before it falls into the black hole, and then accelerate the remaining matter and to eject it into the interstellar medium. In such a case, you could expect to have electromagnetic counterpart in a kind of Kilonova-like counterpart. I guess you will have less matter ejected in such neutron star black hole scenario than in neutron star merger, because you have two neutron stars, you have double more matter, let's say. And I think the process of binary neutron star merger is more efficient in providing ejecta after the merger. So for neutron star black hole, it highly depends on the way the neutron star is falling into the black hole, actually.
It's very interesting.
Yeah, very interesting.
Yes.
And neutron star black hole mergers, we don't have so many candidates, so they are all interesting, actually. So we will send alerts for all those guys also, even if we are less sure that we will have counterparts, but they are interesting.
And we have the possibility to make the difference through the diverse black hole origins.
You mean in terms of mass, things like that?
Yes.
Actually, yes. The gravitational wave what is very powerful actually in the gravitational wave detection, that it gives you directly the mass of the object, because the gravitational wave signals, they highly depends on the mass of the two objects that are going to merge.
Yes.
And you also get the mass, let's say, I say it as simply as I can, but you also get the mass of the remaining object. So you know that what were the two mass of the original black holes, and you know the mass of the remaining black holes, which is very interesting. You also know the spin of the black hole, if I remember well, whether the black holes are spinning or not, something like that. What you have also, which is very powerful in astrophysics, it's that you have a direct distance estimator. So you know the distance at which the merger has been produced, because the distance is going to modulate the gravitational wave signal. So the gravitational wave signal depends highly on the mass and also on the distance of the object. And so you can estimate these two very, very important parameters directly from the gravitational wave data. And having distance in astrophysics is a very rare and a very precious information because it gives you directly the energy that has been released also, not only the flux, just the energy at the source. So that's wonderful information for us. Not only for black hole people, but also for electromagnetic counterpart people, because we can tell you what would be the apparent magnitude of the kilonova if we know the distance, which is a very precious information for follow-up strategy.
Okay, thank you very much.
Thank you.
Maybe one last question. Hi.
Yes.
Sure.
Yes, we are going to take one last question. If you have one last, if you don't have. Spins are not well constrained. Thank you, Pierre Alexander. So this is, in this case, you can see I'm not a gravitational wave expert. Hopefully in QandA we have gravitational wave experts. So I see no other questions, so we can close this very long meeting. I hope you have found it interesting, and you have found information very interesting, and that will help you to better understand the context of this gravitational wave astronomy and this science, and also how to make the follow-up observations. We will try to have closer meeting contact than we had by the past. It's been a while that we didn't have such a meeting, so I will try to keep the 2 months meeting alive as long as I can. Thank you very much all, and have a good night for those who are in nighttime, and have a good day for others. See you all in Slack and by mail, and we'll send you the link of this video of this meeting and the updated slides also probably in beginning of the next week. See you guys.
Very good. Thank you, Damien.
Bye.
Bye. Thank you, Damien.
Bye,
Merci,
everyone.
Damien. Très belle présentation.
Bye, Dato.
Merci, Sarah.